All right, we're back. We are on page 9 of notes, whatever, 16 of Calc AB. We're talking about definite integrals, and now we're going to start talking about basically what the next set of notes is all about, accumulation functions. I love accumulation functions. They are really neat. They give you the ability to like find values of a function without really explicitly knowing the function. So what's an accumulation function? It's basically a function that has an integral in it. What's a differential equation? It's an equation that has a derivative in it. An accumulation function is a function that has a definite integral in it. They're like not really related, but like they feel like they might be. I guess they're related. Everything's related, so I don't want to just say they're not. But so here's our accumulation function. We're going from 1 to x of t root t squared plus 1 dt. That's weird. So to find a value of this function, like if I say find me f of 2, f of 2 is a definite integral. You have to do the integral from 1 to 2 of this thing. What's f of 10? Well, it's the integral from 1 to 10 of this thing. So it's like a lot of integrals, but fortunately, we're going to use a calculator for a lot of it. So use your calculator to fill in the table for f of x, -2, -1, -2 through 4. So let's switch to the calculator and let the calculator do its thing. So over here, all right, so I'm going to just do a new document for me, f of x. So your calculator doesn't care, just put it in. F of x is the integral from 1 to x of t times square root of t squared plus 1 dt. All right, now I got to find f of -2, and we need decimals, so -2, -1. Oh yeah, -1. Does -1 make sense? Is this thing odd? Oh, I think it's odd. Yeah, I think so. Like -1 to 1 would give you 0. 0. So I'm going to start filling these in. 3 decimal places in the table. Everybody fill them in along with me. 2.784, 0, -0.609, and then we need 1, 2, 3, 4. 1 to 1, obviously, should give you 0, 2, 3, and 4. So 0, 2.784. Oh, because this is, wait, is this odd or is this even? It's odd. It's, oh, well, that brings up an interesting question about like even and odd functions, but now's not the time, so don't talk about it. 9.598, 22.422, 22.422. All right, so I filled those in. Next thing it says is use your calculator to graph it. Okay, so doc for graph f of x. Sometimes it takes a little while with these, but there you go. All right, looks like function. It's an even function because the function itself is the integral, right? So you have to do the integral from 1 to x. The integrand t root t squared plus 1, that's odd, right? So is it the case that when you integrate an odd function, you get an even function? I don't know, try to work it out. Is it the case that when you take the derivative of an even function, you get an odd function? How about an odd function? Do you get an even function? Try to work those things out. So we have this. So now it says find, I'm going to do the next part by hand, but your calculator could definitely just do it. It says find a form that does not involve an integral. So I'm going to just like use a fundamental theorem. So the notes point out, this is insane. You usually cannot do this. It's like very unusual to be able to do this. Usually the integrand is just some gross thing that you're like, no one could find an antiderivative for that. But in this case, I think we can because we want to do the integral from 1 to x of t root t squared plus 1 dt. So I look at it and I'm like, well, if I make this u, there should have been a 2 here, so a 1/2. And then it's to the 1/2, so 2/3. And then t squared plus 1 to the 3/2. And it'd be plus c, but this is actually a definite integral from 1 to x. So this is 1/3, and then x squared plus 1 to the 3/2 minus, when you plug in 1, you get 1/3 of 2 to the 3/2, which is kind of gross, but I mean, that's what it is. So the next question is, so this is f of x. All right. So you may have noticed, you may have thought about this, or you may not have. This number was 1, and like that's fine. And when I plugged in, so I plugged in x and it gave me like this part. So no matter what this number is, when I plug in x, it will give me this part. When I plugged in 1, it gave me this. If I plugged in like 58, it would just give me like some other number here. That's going to be really relevant. And then think about like this as your kind of like a vertical shift versus, you know, plugging in 58 as a vertical shift. Like they'll have a different vertical shift depending on this number, but like they're all basically the same function. They're all basically this function with various vertical shifts. Going to be super relevant. All right, let's find f prime. So f prime of x is, well, the derivative of this is 0, so that's just gone. This, I'm going to bring down the 3/2, so I get 1/3. 3/2 x squared plus 1 to the 1/2 times 2x. And if I simplify this, I get x radical x squared plus 1. Have you seen something like that somewhere? I think you have. Look at the original function. The original function had this as the integrand, and this is the first derivative. And does that make some sense to you? That makes sense to me, because so I'm integrating this to get the function. So if I take the derivative of what I found, I feel like I should get back to this. And that's what happened. It changed the variable from t to x, but that like kind of makes sense to me. The second derivative we're just doing for practice because it really has nothing to do with this. So f double prime first, what's the derivative of the second? I think it's x over radical x squared plus 1. So it's like 1/2 the thing to the negative 1/2 times 2x. 1/2 and 2 cancel, you get x over the radical. And then plus radical x squared plus 1. Common denominator, x squared plus the quantity x squared plus 1 over radical x squared plus 1. So f double prime, again, there's like not really, other than practice, there's no real reason to do this. X squared plus 1. That, I believe, is our second derivative. And then, so think it through, right? What did we say we thought would happen for this next thing? So now it's from 0 to x instead of 1 to x. So look at, so g of x is the integral from 0 to x of t root t squared plus 1 dt. It's an accumulation function because it has an integral in it. F of x is the integral from 1 to x of t root t squared plus 1 dt. So what if I subtracted f of x minus g of x? What if I do that? F of x minus g of x. So I'm going from like, we can do our bar thing, right? We're going from 0 to x is kind of f. And then g of x is 1 to x. I'm just assuming x is bigger. This is g. So this, what was it? This is 0 to x. And then this is 1 to x. So if I do f of x minus g of x, it should give me the integral from 0 to 1 of t root t squared plus 1 dt, which is just a number, right? They're just vertical shifts of each other. And the vertical shift is weird. It's the integral from 0 to 1 of t root t squared plus 1. So what I'm going to do is I'm going to go to the graph and take a look at that. I'm also muting and unmuting myself so I can watch the stupid sound thing. I don't know. It's so annoying. It's annoying when anything doesn't work the way it should. So on my graph page, I already have a graph page. Graph page here. And then, so I want to graph the integral of t square root of t squared plus 1. T is a variable. This time I want to go from 0 to x. 0. I should have done I think g of x. I should have done g of x minus. I've like flipped it in the notes. I'm going to go back and change that in a second. Okay, so this is above this. And like, how far above is it? We think that it is, if I do let's see what happens here. F2 of x, what is F2 of x? F2 of, let's go back. Okay, so F2 is g of x, and F1 is f of x. So if I do g of x said equal to F2 of x, if I do g of x minus f of x, I get this. I think that that's the integral of t times the square root of t squared plus 1, where t is a variable, from 0 to 1. And it is. So that's all the differences. So if we did like from 5 to x, it would be a vertical shift, and the difference would be the integral from 1 to 5, because that's how different they are. So I need to go back to the notes and fix something, but like we're basically done. The whole entire next set of notes is about accumulation functions. So you're gonna get your fill of them. They're everywhere, and they're really cool. So like not gonna be a big problem. So this was flipped, I think. So this from 0 to, this is g of x and this is f of x. So if I do g of x minus f of x, it should give me the integral from 0 to 1. G of x minus f of x, which is basically telling you that since that integral is going to be positive, it's telling you g of x is above f of x, which we saw when we graphed it. So they're just vertical shifts, very cool. If they're vertical shifts, they should have the same derivative, right? And I think the derivative of both of them is going to be x square root of x squared plus 1. So I think that's the derivative of g of x, f of x. If we had the integral from 2 million to x of t root t squared plus 1, the derivative would still be x root x squared plus 1. Very cool idea. We're going to talk about it a lot more in the next set of notes, and I will see you there. So I don't know. That's the end of these. Hope you're finding them helpful. See you in the next.